Okay, so good evening, everyone. Am I audible? Anirudh, am I audible? Okay, good evening, everyone. Am I audible? I think let I am waiting for 5 minutes, and then after I will start. We just I am waiting just to see anyone is joining or not. So okay, just 2 more minutes. I am waiting. If anyone wants to join, then I will start. Okay. Okay, it's already 6:05. So now I can start. Okay, so that's okay. Good evening, everyone. Myself, Amiya Mandal. I am a PMRF scholar of IIT Roorkee, and I am working under Professor K. Yadav in IIT Roorkee in Physics Department. In this lecture, I am doing teaching assistantship duty of PMRF in a NPTEL course. NPTEL course name is Fundamentals and Applications of Dielectric Ceramics. I am going to start my assignment 3 problems, and it's regarding question, answer, and solutions. This will be done on the basis of week 3 assignments, problems, and questions. And the course instructor of this course, NPTEL course, is Professor Ashish Ghai from IIT Kanpur. So we can start. First of all, in week 3, what you have learned in week 3 are those. These you have already learned in week 3. Some intrinsic and extrinsic defects, some defects and defects equilibrium. Okay. So you have already learned in week 2, week 1 and 2. In week 1, some crystal structure. In week 2, how many types of defects. And here you have learned about intrinsic, extrinsic defect, some homogeneous and non-homogeneous defect, stoichiometric and non-stoichiometric defect. So first you have learned intrinsic, extrinsic defect in week 3 also, and all the problems will be based on in week 3 what you have learned in week 3. Okay. So, and defect concentration in non-stoichiometric oxide. Okay, you also have learned this. Intrinsic ionization in metal oxides. You also have learned this. Brouwer's diagram, where partial pressure of oxygen, how they affect oxygen vacancy defect and concentration of electrons, concentration of holes, everything you have learned. And we also see the problem based on this topic. Okay. Also, and after that, some introduction of dielectric ceramics have also been taught in week 3. Okay, so we can now go forward to week 3, question number 1. Okay, let's just checking whether everything is okay or not. Just wait for some time. Okay, everything is okay. Okay, so question number 1 first. Okay, so question number 1 is small scale non-stoichiometry. So non-stoichiometry in a metal oxide. Okay, you have already learned about non-stoichiometry in metal oxide, stoichiometry in metal oxide. This is mainly the defect in stoichiometry, stoichiometric defect or non-stoichiometric defect in where metal oxide, metal oxide. Okay, so you all already have learned about this. I'm just discussing some points so that you can answer the question. But this is the small scale non-stoichiometry. Okay, so let's see what is the stoichiometric metal defect, metal oxide defect, and non-stoichiometric metal oxide defect, so that you can answer this question. Okay, so I'm just briefly discussing about the stoichiometric compounds, and its intrinsic point defect. Okay, intrinsic point defect. It can be classified into five different classifications. First of all, you already have learned in previous lectures also that Schottky defect, anti-Schottky defect, Frenkel defect, anti or anion Frenkel defect. Okay, where anion involves in Frenkel defect, it called anti-Frenkel defect. Mainly, in Frenkel defect, cation vacancy and interstitials are formed, and anti-side defect. Okay, so these are five defects. I am just briefly explaining this. So what the Schottky defect tells us about? Schottky defect is cation just like Na and Cl minus. The bigger ion is Cl minus. You already have learned the cation and anion position of sodium chloride and its unit cell position and its sodium and chlorine position in a unit cell. Okay. Sorry. So what is the Schottky defect? Schottky defect is cation and anion vacancy. Here you can see this is sodium and cation, and this is where uh, anion vacancy, this is chlorine vacancy. So if both these sides simultaneously are absent from a unit cell of sodium chloride, then the Schottky defect arises. This type of defect maintains stoichiometric ratio. What is the stoichiometric ratio? Stoichiometric ratio between the radius of cation and radius of cation ratio. Okay, this always maintains here. So this is a stoichiometric compound. Stoichiometry of this compound remains present in this compound. And what is anti-Schottky defect? Where cation and anion interstitial, but not common. Here in this side, and this is the interstitial position. One is one you know about the side and one you know about the interstitial position. Okay, these are the side position and this is the interstitial positions. So if this defect found in interstitial position, then we will tell that anti-Schottky defect. But here stoichiometry is also conserved here. Okay, stoichiometry cannot be um, disturbed. Okay. Next is Frenkel defect. These are two scientists, Schottky and Frenkel. After them, this name has also been adopted after Schottky and Frenkel defect. Okay, so next is Frenkel defect. We already have learned that Frenkel defect when metal interstitial, cation vacancy or interstitial. Here you can see that one cation, that is sodium plus ion, has been moved to the interstitial position, okay, to this interstitial position. So this type of defect, we can tell it as a Frenkel defect. What is the anti-Frenkel defect? Anti-Frenkel defect is anion vacancy. This, in the previous cases, we have seen that sodium is occupying the interstitial side. But if this anion, chlorine, occupies the interstitial side, then what we can say? This is anti-Frenkel defect. And anti-side defect. Cation ions swap if they don't swap. Okay, then it is anti-side defect. This is not too much important. So all this tells about the stoichiometric compound and their properties. Now, what's the non-stoichiometric compounds and what is its property? Non-stoichiometric compound is telling that do not have simple integral ratio of atoms. That is the very important point. They do not follow the ratio of cation and anion. Just like sodium chloride and silver chloride formed here, this is the silver chloride and this was the silver chloride. Okay. In case of Schottky and Frenkel defect, we have seen that the cation and anion ratio was maintained. Okay. But in this case, they do not maintain. So what will happen here? What happens there? Metal deficient, metal excess, oxygen deficiency or oxygen excess. So metal oxide, one is metal, one is oxide. It can be excess or it can be deficient. Okay. Then this type of non-stoichiometry arises. And if oxygen, in case of oxygen, it may also arise. And in both cases, they also arise. Okay. So this type of defects are called, this can be plus delta, this can be minus delta. As we can see, metal deficiency. Deficiency means metal from its metal position, some metal cations are less from its side. Then just like cobalt oxide 1 minus X, nickel 1 minus XO, iron 1 minus XO, these types of materials, so non-stoichiometry metal deficiency defect. And again, what will be the metal excess defect? Cadmium oxide. This is very important. And cadmium oxide is a material excess oxide. Okay. And everything, deficiency and excess of metal anion cations depends on what? Depends on their binding energy, depends on their ionization energy. If something has less ionization energy, it show metal deficiency. If anything has ionization energy greater than its some another compounds which I am doping, then it shows metal excess. So similarly, in case of oxygen, also this properties has also been shown. If oxygen anion are less from its site, then 2 minus Y here, this zirconium dioxide, cesium dioxide also showing metal deficient oxide. Okay. And what is oxygen excess oxide? Metal, if uranium dioxide. Okay. So these are some examples, and here we can see that some compounds so that ranging from their how ranging of X means in which range they can metal excess or metal deficient or oxygen excess or oxygen deficient behavior shows. Everything has been listed for some material, and I am just discussing material that is iron oxide. Okay. Iron oxide, if iron oxide is heated, iron oxide mainly shows metal excess. We have seen it. Okay. Sorry, metal deficient. So X is less than 1. It must be less than 1. So vacant cation. Vacant cation side will be formed here. Just like this equation is follows. Iron is and this iron side is compensated by Fe3 plus ion. Okay. So ferrous ion So ferrous is transforming into ferric. This is called ferrous and this is called ferric. Okay, this is ferric. So this type of behavior is shown in iron oxide. You can see here that uh, this is ferric. Ferric. This is filled by the in the vacancy of this Fe2. So here Fe2 vacancy has been created earlier. Fe2 vacancy earlier created, and it is filled by this iron means ferric. So in these cases here, so in cases, what is happening here? This is metal valency. Valency 3 plus is greater than 2 plus. Metal valency is increasing. Okay. So this is the case of, and here you can see this iron cation is deficient. Okay. Here you cannot fill this side. Okay. So to compensate for smaller number of cations and consequent losses of positive charge, two Fe2 ions must be transformed into Fe3 plus ion. Why? For each vacancy form. Okay. So in these cases, we can see this type of material replaces iron oxide, in which vacancy of Fe, this is vacancy, okay? This vacancy of represents a vacant cation side. Okay. So to first approximation of ions may be considered as a distributed at random. Okay. In this regard, Vegard's law is more important here for iron oxide. This is metal deficient oxide. Okay. Metal deficient oxide. What Vegard's law said? Vegard's law is very important to learn to answer the question number 1. Okay. For most of the non-stoichiometric compound, their unit cell size varies smoothly with composition, but symmetry is unchanged. Symmetry do not change. Means the actual structure is obtained whatever the cation position changes or cation charges has been changed. Also, charge is also changed. So charge, uh, what properties has remained constant? Charge and size, structure remains constant. Okay. So varying, what do we vary here? What is varying here? Varying is iron oxygen ratio. If we do iron, Fe3, ferric in the ferrous ion. So ratio will vary. It is increasing. It is increases. Okay. And the corresponding iron ratio is decreasing, iron oxygen ratio. So mainly radius ratio of Fe, radius ratio of oxygen varies. Okay. And density is varying. This is also why density is varying? Because the corresponding lattice parameter is varying. Exact volume is constant, but why density is varying? Because the lattice parameter, mass is constant, but volume is varying. That's why density is varying. Okay. So density is varying here. So, and there I have collected this data from this source. So we have learned about Weger's law, non-stoichiometric compounds and stoichiometric compound. You can now easily answer this question that small scale non-stoichiometry in a metal oxide results in what? First option, that deviation from stoichiometric cation and anion ratio. This is true. Next, crystal structure changes. No, that's not true. Crystal structure remains stable, remains unchanged. Okay, so this is not true. Deviation from electrical neutrality is also conserved here. So this also not true. And density must change due to the changing of the lattice parameters. We have seen some examples of iron oxide. Okay, so density changes. So two options are correct. So that's all from question number 1. We can now move forward to question number 2. Question number 2 is telling about oxides like aluminium oxide and magnesium oxide. Magnesium oxide, aluminium oxide. What the charges of aluminium? That is +3 charge, valency. Okay, oxygen -2. What is the charges of valency? Sorry, this is -2. Okay, so a very small range of non-stoichiometry. So they are also metal oxide. They also show non-stoichiometry. Okay, but in a very small range. Why? What is the reason behind that? So, okay, so options are cations have a very small value of ionization potential. Cations have very large value of ionization potential. I have previously told about the ionization potential. If some cation possesses very large ionization energy, ionization potential, so it cannot accept any anion in its site, so that to unstable its position, to unstable its site. So ionization potential must be a very important factor. It should be very large to show very small range of non-stoichiometry. So this is the correct answer. Okay. Ionization potential must be very large for very small range of non-stoichiometry. Means to show less non-stoichiometry behavior. And C option, large energy for defect formation and small energy for defect formation. Defect formation energy should be very small so that it will show non-stoichiometry. Okay, so this is the small energy of defect formation. Sorry, large energy of defect formation. This should be large energy of defect formation. Defect formation energy means the amount of energy required to form defect inside the material. So defect formation energy in this case of aluminum and magnesium oxide is very large, so that it is showing very small amount of non-stoichiometry. Okay, so this is the large amount of uh, defect formation. Here you can see that some metal oxide, okay, metal oxide compounds and their composition range. We can see titanium dioxide, vanadium, manganese, iron oxide, cobalt oxide, nickel oxide, selenium oxide, zirconium oxide, uranium oxide, okay, etc. All these have, all these are varying very large range. You can see here, large range. Not just like, unlike, not in the case of aluminum oxide, manganese dioxide, they do not vary just like this. Why? Because of their ionization potential and large defect formation. Okay, so oxide in general show variation of composition with oxygen pressure. We see, and we also have learned about oxygen pressure, the um, importance of oxygen pressure in creating non-stoichiometric figure and non-stoichiometric compounds. We also have learned, I will tell also in later, like a question, when question arises. Next is stable oxides having a cationic presence for a single valence state, a high ionization potential. This is very important. Single valence state with a high value such as aluminum oxide, magnesium oxide. All these materials shows single and stable valence state. Magnesium shows +3 valence state. Magnesium shows +2 valence state. But these materials show variable valence state. Just like iron, it shows +2, +3, +1, okay, +5, 4, 5, etc. So these are varying. So we cannot compare them with stable and variable ionization state, valence state. So this is also a reason have limited range of non-stoichiometry, and in this materials subset, non-stoichiometry effects are very often related to impurity contents. So if any material, any sample contains any impure um, another impurity in its sites, and just like we have seen in aluminium, sodium chloride, then this shows a different kinds of behavior, Okay, next is oxide of cations having a low ionization potential can show extensive region of non-stoichiometry. So, to show extensive region of non-stoichiometry, there should be a low ionization potential so that any uh, mm, external cation can replace this site and show defect and show non-stoichiometry in the solid. And here I have listed some ionization potential to show that the ionization potential is very large for aluminum and magnesium. This is the first, second, third ionization potential. You can see it is approximately from 5,000 to 2,000 kilojoule per mole. This is very high. Okay, this is very high ionization potential. Here is some information about the defect formation energy. Defect formation energy, you can see that there is a comparison between magnesium oxide and sodium chloride. You can see that magnesium oxide has defect formation energy up to 7.7 electron volt. But in case of sodium chloride, the defect formation energy is 2.4 electron. You can see the difference. How magnesium energy has larger defect formation energy um, in respect of sodium chloride. Okay, there is some so in this affects also the melting point. So magnesium oxide has melting point of 2825 degrees centigrade due to its defect formation and a large defect formation energy. And the defect formation. Okay, so NaCl shows a much larger defect formation. Okay, so we can now answer the question that this is the confirm. We can confirm now. Confirmly said that um, cations have a large value of ionization potential and large energy for defect formation. Okay. Question number 3. Cobalt oxide has the tendency to metal deficient. Okay. Metal deficient. Okay. Why? Identify. So in case of what is the metal deficient? We have seen in iron oxide also. Okay, metal deficient oxide. So this is the defect equilibrium reactions. Defect equilibrium reactions. Okay, equilibrium must be balanced in these cases. Where three things must be remembered in case of balanced equilibrium state. What are three things? First of all, mass balance should be there. Second, charge balance should be there. Third, side balance should be there. Okay, so balance should be there, and the mm, uh, concept for metal deficiency should also be known. You have to know what is the when a metal deficiency is created. Okay, so metal deficient oxide, MO type oxide, with deficient of metal, which can be reflected either metal deficiency or oxygen interstitial. Metal deficiency or oxygen interstitial means MO. In case of metal deficiency, M1 minus delta, or you can say oxygen deficiency, that is oxygen interstitial. These two can be, so these two can be possible. Okay, these two can be possible. Okay, that's why they told that metal vacancy and interstitial or presence of both. Metal vacancy, oxygen interstitial, or presence of both. Okay, so what is the metal deficiency equilibrium? What will be the equilibrium for? So In case of oxygen, what will be the oxygen size deficiency? It would be what? Um, for first of all, assuming complete ionization of vacancy, we can write half oxygen. This is the metal vacancy. Metal vacancy will be created and two holes will be created. Metal vacancy, this means this is the Kroger-Winch formula where this is the metal site where is a vacancy is created and with two unit negative charge. So unit negative charge is compensated by two holes. So balanced reaction. This is the balanced reaction. So uh, this option is correct. There may be one or two more options be correct in every question. So we can also see, we must have to see another three options also. Okay, so that to answer this, we now proceed to forward. We are now proceeding forward. So what is the equilibrium constant? You also know the how equilibrium constant can be found. This is the concentration of oxygen, concentration of metal vacancy, and concentration of whole concentration and its square. This is the partial pressure of oxygen. This is very important. When in stoichiometric oxide, no partial pressure was uh, created or no partial pressure was required. But in case of non-stoichiometric oxide, partial pressure of oxygen is required. Partial pressure of oxygen is um, we must calculate, we must conserve, we must uh, take the partial pressure of oxygen concentration or its contribution in defect formation, we must have to consider. Okay. So these are the initial conditions that the oxygen, this is the oxygen concentration, metal vacancy concentration. Okay, and this must be less than this. So these I am not going to details all of this. So these all have you have learned, and for electrical neutrality, this will show. And this concentration defect is proportional to this. Okay. Hmm. Now, this is the case of metal deficiency defect. Okay. Okay. Now, one can do similar exercise for the cases of oxygen interstitial case. Okay, can do. This is the case of metal deficiency defect in nickel oxide. You can see that one nickel ion is missing in this place, creating a vacancy in this place at its relative side. And to fill this vacancy, the deficiency of the two positive charges is made up of the presence of two nickel Ni3 plus ion. Two nickel 3 plus ions will be there. At the other lattice site of nickel 2 plus ions. For the composition nickel junction, then this will be for okay. Nickel 1 minus 0.03 will be there and oxygen 9.0 will be there. Nickel oxide. This is the case of nickel oxide. I have just taken an example. So what will be the in the case of cobalt oxide? This already we have already seen in cobalt oxide metal vacancy and its corresponding hole. Similarly, the absence of an electron normally present in the stoichiometric state corresponding to electron hole composition. So this is also true. Means cobalt vacancy and a unit negative charge in two possible cobalt vacancy. Okay, as we have seen in nickel oxide. We have seen in nickel oxide that two unit positive vacancies, two, two positive charges made up of the presence of the two nickel ions at other lattice side. This is very important. This should be applied in the cobalt oxide also. Cobalt oxide also. Okay. So in this cases, two cobalt vacancies also created at there and with their unit positive, unit negative charges. unique positive charges. Okay. So question number, option number 3 is also, 4 is also correct. Okay. Any problem? Just I'm seeing that everyone are present or not. Okay, everyone are present. Okay, recording is going. Everything is fine. Now, okay, this layout is also fine. Okay, okay, we can now forward to next question, question number 4. That is for the reaction MO. This is the reaction, metal oxide reaction MO, where metal is at metal is fixed at metal position. Oxygen vacancy is created here. So here main factor is oxygen vacancy. Okay, oxygen vacancy is main factor here. So oxygen vacancy is creating here with oxygen is emitting out with two electron left. Okay, so what would be the true here? This is the case of oxygen vacancy, a dominant defect. Okay, what would be the reaction? Reaction is this, and the corresponding reaction constant will be this. This is the case when this is the non-stoichiometric defect equilibrium case, and reaction constant is this, and partial pressure of oxygen is similarly important here with in the reaction constant. I am not going to tell all the details now, but what is the important case here? How electrical neutrality is maintained. Electrical neutrality is maintained for each vacancy site. How each vacancy site is will be compensated by each vacancy of oxygen will be compensated by two vacancy site with for um, electron neutrality, electrical neutrality. So N equal to vacancy of oxygen. Okay, this is the form. This is the condition. So what will be the answer? The answer will be this. Two vacancy site will be involved here for compensating the electronic concentration. Okay, so using this formula, you can just see that using this formula, this has been um, forwarded K value, and how Ne or Vo is dependent on K value, you can see here. Okay, so this is the variation of um, log of vacancy concentration of oxygen vacancy concentration and log of partial pressure of oxygen. Okay. Log of partial pressure of oxygen. All these are all these should be maintained. Okay. So now we can. So this is defect formation, concentration versus partial pressure of oxygen in an oxygen deficient oxide with oxygen vacancy as a dominant defect. Okay. So in this perspective, for case 1, when oxygen vacancy are dominated in metal oxide defect, when oxygen vacancy is dominated, we can easily answer the question. I am just uh, discussing some more cases. If metal interstitial or metal excess is present, what type of behavior, what type of equilibrium equation should be there. I'm just briefly telling about. This is the case of interstitial of metal or metal excess. If metal stress or metal interstitial are present, what will be there? And what will be its variation of depending of oxygen partial pressure with oxygen vacancy or metal vacancy or electronic concentration. Okay, so I'm just not going to details, and this is the equilibrium equation where metal interstitial side are formed. Metal interstitial. Okay, interstitial. Okay, this is forming, and the corresponding electron will be formed. So this partial pressure of oxygen will be there. Okay, so what, and here for metal vacancy, what will be there? Metal vacancy, metal interstitial, what will be? Metal is occupying at the interstitial side. So similarly, we have seen in the case of oxygen vacancy, similarly in this case also, the interstitial cases also, the electron concentration will be uh, compensated by two more oxygen metal interstitial. Okay. So this is how varying. This is how in metal interstitial site is varying with partial pressure of oxygen. We can see that it is varying with N. N varying with partial pressure of oxygen in minus to the power 1 by 6. Okay. So this should be remembered because I am telling, because the next question which will be asked, you can see these types of equation and how metal, how electron concentration is varying, means how partial pressure of oxygen is related, or how partial pressure of oxygen is involved in electron concentration, and metal interstitial formation and vacancy formation are varying in case of when metal excess are seen, and in case of oxygen vacancy are created. So partial pressure of oxygen, how they are varying. Okay. And case 3, we have seen oxygen vacancy case. We have seen metal interstitial vacancy cases. And case 3, where both are simultaneously created. Simultaneous presence of oxygen vacancy and metal interstitial. What will be the equilibrium equation? What will be the contribution of partial pressure of oxygen? You already have learned it. I am just recapping all those things. That just like such a scenario is often found this when both of these are present. In which cases? Titanium dioxide and niobium pentoxide. These materials are oxygen vacancy rich materials. Niobium pentoxide is also. Okay. So these types of material shows oxygen vacancy as well as metal interstitial. Okay. So in these cases, we have to assume this, that oxygen vacancy and metal interstitial, metal at metal, the concentration we have to assume as 1. So what will be the defect equilibrium condition, just like for K1, K2. K1 is for oxygen vacancy, K2 is for metal interstitial. And what will be the electrical neutrality here? Means how electrical neutrality should be conserved in every type of material. In case of stoichiometric and non-stoichiometric, electrical neutrality must be conserved there. So what will be the electrical neutrality condition? Condition of electrical neutrality is 2 VO. Here 2 vacancies of oxygen, just like titanium dioxide, and 2 metal interstitial. It depends on materials to materials. It may be 2 VO plus 3 metal interstitial. Okay, it depends on material. Okay, I'm not just discussing all about this, what will be the material and what will be this. I'm just telling that electrical neutrality should be conserved here. Okay, just like here, AMO is conserved here. AMO is told where oxygen vacancy valency is -2, and there should be metal vacancy. That's why it is taken two oxygen vacancy and two metal oxide. That, sorry, metal dioxide has been taken here. Metal oxide has been taken here. So this should be maintained. Okay. Now, this limiting cases, two limiting cases has been discussed here. First of all, if there is oxygen vacancy and metal interstitial. Okay, these two are formed. Sorry, metal interstitial with two unit negative positive charges, where oxygen vacancy with two unit positive charges. So these two has been created. Okay, so limiting cases, if only oxygen vacancy is much greater than the interstitial set, what will be there? Their corresponding uh, oxygen vacancy concentration and metal interstitial concentration will be changed. You can see it is varying. This is the constant. K value is constant. K is what? K is proportional to exponential of minus delta HF divided by twice K T. Okay. So this is constant because delta HF is constant, K is constant at a particular temperature, that is also constant. So we are not interested in K. We are interested in how this oxygen vacancy and metal vacancies are varying with partial pressure of oxygen when, what is the limiting case? Limiting case is when the oxygen vacancy is much greater than the metal interstitial. Okay, metal interstitial. So here how metal interstitial is varying, how oxygen vacancy is varying with 10 to the varying with partial pressure of oxygen with -6 to the power -1/6. But in case of metal interstitial, it is varying with to the power -2/3 in case of MO2. Okay, it depends on materials to materials. Okay, here I am just I have just taken an example so that we can I can clearly tell that the concept of variation of oxygen interstitial, metal interstitial, and oxygen vacancy. So you can see, so 2/3 is greater than 1/6, right? So you can see that this decreases more rapidly because some denominator, sorry, this is, so decreases more rapidly because of this with increasing PO2. This is commonly observed in titanium dioxide and neodymium dioxide. Okay, so what will be the main factor here? Main factor will be the oxygen vacancy, not the metal interstitial, because it is decreasing, okay, due to the partial pressure of oxygen. Similarly, what will be the case of metal interstitial if metal interstitial greater than the oxygen vacancy? Okay, here this vary will continuously and this will vary 1/6. Okay, this is positive and this is negative. Means when this increases, it is, when this decreases, it is increasing. When partial pressure of oxygen is decreasing, it is increasing. So the factor is more important here. Metal interstitial factor is more important here. Oxygen vacancy increases with increasing PO2 while, so this is increases with increasing PO2 while keeping distance of PO2 but at different rate. Here you can see defect concentration versus PO2 graph. Okay, that uh, how this is how metal oxygen vacancy decreases this type of figure, where this slope decreases. This is the graph between log VO and log PO. This slope -1/6. This is the slope of -1/6. Okay, and -2/3. There was -2/3 there. This slope is greater than its minus slope. This slope is greater than metal interstitial. Okay, so here this is very uh, significant. This was very significant oxygen vacancies there. So this graph follows this type of reaction. Similarly, for metal interstitial, this is with follows here. And this is the N value. N is what? 2 of oxygen vacancy into 2 of metal interstitial. Okay. So this is just multiplication of these two. So it will follow these types of graph. Okay. So that's all. So you can easily understand that you have already understand that the non-stoichiometric cases, how oxygen vacancy and metal interstitial are the some measurable factors and some important factors for any non-stoichiometric materials. And that's why I have already I have discussed for oxygen vacancy, metal interstitial, how their partial pressure of oxygen. You already have learned it in your weekly lectures. I have just recapped all of this. So from this concept, you can easily answer that this this will be the correct answer. That N equal to twice V naught V oxygen vacancy at with 2 unit positive charge. So based on these concept, case 1, case 2, case 3, as I already have discussed every concepts, you can easily answer question 5, 6, etc. Okay. So what question 5 tells us about? Similar reaction has been given. Question is different. The reaction is MO metal oxide. Metal is situated at metal position. Oxygen vacancy is creating. So oxygen is emitting out, creating a partial pressure of oxygen. Okay. This is affecting how this partial pressure of oxygen is affecting the material with 2 electronic charges. Question is, the concentration of oxygen vacancy is related to which? Concentration of oxygen vacancy is proportional to PO2. Okay. Concentration of PO2. Okay. In which proportion? What is the value of X? Okay. You have already learned it in question number 5 discuss. Question number 4 discussions. I am going again to question number 4. Oxygen vacancy is forming. Okay. You can see these types of reaction where metal is fixed. Metal is fixed at this position. This will happen that metal is fixed at metal position. This is the reaction. So this is the reaction constant where oxygen vacancy, concentration, electron density, electron concentration, and partial pressure of oxygen concentration will be there. Using this relation, we have calculated all this, just putting the oxygen vacancy, just subtracting the oxygen vacancy density with Ne. And the corresponding graph tells about log of V and log of PO2, showing the N value of oxygen vacancy value, and this is PO2 to the power -6. PO2 to the power -6. Okay. So what will be the value of X in the question number 5? What will be the value of X? The value of X is what? To the power -1/6. This is the correct answer. To the power -1/6. Okay. Now we can move forward to question number 6. That silver iodide. This is the metal halide. Okay, this is metal halide. This is the halide, not oxide. Okay, this is halide compound, which is showing Frenkel defect. This is a what is Frenkel defect? Is stoichiometric defect. Stoichiometric defect means where charges, mass, and site ratio should be conserved. So, in case of metal halide, silver iodide, question is telling about that information is given that silver iodide is prone to having Frenkel defect. Okay. Uh, is everything fine? I am just checking. Okay, recording is going on. Um, okay. If any question arises, you can tell. Okay. Um, okay, I am again starting the question answer session. Just wait for 1 minute. I'm just changing the layout. The layout is fine. Um, okay, that's fine. Okay. So question number 6. Uh, okay, so silver iodide is prone to having Frenkel defect. Silver iodide is prone to having Frenkel defect. Frenkel defect. So you already have learned about the Frenkel defect. What Frenkel defect is? Frenkel defect is nothing but the movement of um, cation or anion from its site position in a unit cell to its interstitial position. Okay. Now the question is what kind of defects are likely to form? Okay. So first option is equal number of iodide vacancy and iodide interstitials are formed, may be formed. Equal number of silver or iodide interstitials are formed. Equal number of silver vacancies and iodide vacancies. Equal number of silver interstitials and silver vacancies formed. So answer will be equal number of silver interstitial or silver vacancies. Sorry, this is from interstitial and vacancy. Okay, right, right. So silver interstitial will be silver will be filled by silver will move to interstitial site and filled with and silver vacancy will be created. And you all know about the Frenkel defect where the cation site is moved to the interstitial position. This is the interstitial position. This was the site position. So this is moving to the interstitial side. Okay. This type of defect is Frenkel defect. You already learned about. But what will be the case of silver iodide? Okay, silver is one positive, iodide is one negative. Why anion is not moving? For the case of anion movement, this we call it anti-Frenkel defect. Anti-Frenkel defect. Okay. Because they do have different ionization potential. Okay, as silver ionization potential is um, less than iodide, so silver has first priority to fill the interstitial ion to show the Frenkel defect. Okay, so the main condition is what? Main condition is uh, the coordination number should be low. This is the first condition. The size of the anion should be bigger than the cation. R of silver should be bigger than the R of Ag. So this should be the conditions to follow the Frenkel defect. And all these conditions are followed by silver iodide. That's why silver is moving to the interstitial side and not the iodide ion. Okay. So the defect is not found in alkali metal halide because cations and anions have almost equal sizes and cations cannot be accommodated in interstitial side. So it is not found in alkali metal halide. Frenkel defect it requires low coordination number, crystal defect point phenotype, and mostly exhibited in ionic solids, where the smaller ion usually cation is dislocated. Smaller ion is dislocated. Okay, smaller ion is dislocated. This is the main important factor. Some examples are those. And this is the unit cell structure of silver iodide. This is the unit cell structure. You can see this is the silver ion and this is the iodide ion. Okay. So silver ion moves towards the interstitial side, this side or any other side. Movement of silver ion is occurred here. I have just shown the unit cell just because of understanding how and which positions the silver ion moves in interstitial side. This is the unit cell structure. And radius ratio factor must be important, as you can see the radius ratio of silver. So this is less. Okay. So that's why it is showing what? Frenkel defect, and silver is moving to the interstitial side, not iodide is moving. Okay. So based on all these uh, concept, we can say that equal number of silver interstitial and silver vacancies will be formed in case of Frenkel defect in silver iodide. Okay. Now we can now move to question number 7. Okay, this is the doping of sodium chloride with cadmium chloride. What will be the defect formation? Okay, I already have told much about the metal excess, metal deficiency, oxygen excess, oxygen deficiency. Okay. Based on this concept, you can also answer these types of question. Okay. I previously told about iron oxide, nickel oxide examples for defect, how the defect formation occurs. Depending on all these, you can also answer sodium chloride doping chloride, cadmium chloride. Okay, just 1 minute. Just okay. So this is the case of metal excess. Sodium chloride, that is +1, that is -1 valency. This has +2 valency. Cadmium, this has -1 valency. Means in case of sodium chloride, in case of sodium chloride, okay, in case of sodium chloride, no, sorry, this will be sodium, this will be sodium, and this will be chlorine. Okay, you can now consider. I am just telling that this if this is sodium +1. Okay, if this is sodium +1, if one side is missing from its position, then it is one metal deficient. But if we are doping cadmium with two positive charges, what will happen? Cadmium with two positive charges. What will happen? So two positive vacancy site of sodium should be there, so that two positive sodium should be vacant there, so that charge should be maintained. Okay, so one cadmium ion occupying this place, Okay, cadmium 2 plus occupying this place. And the regarding chlorine atom occupies at the interstitial position. In which position? At interstitial position. So these types of behavior will occur. So chlorine interstitial should be formed there, and uh, one sodium vacancy should be there, as one site is occupied by the cadmium. So one sodium vacancy should be there. One sodium vacancy should be there, and one chlorine interstitial should be there. Just I'm just mm, explaining some point defect, condition, Schottky defect, Frenkel defect, and non-stoichiometric defect. This is some tabular explanation of what types of defects are classified in stoichiometric defects and non-stoichiometric defects. In stoichiometric defect, we already have learned about Schottky defect, Frenkel defect, interstitial defect, this type of defects in preventing Schottky defect in NaCl when equal amount of sodium and chlorine simultaneously are absent from their side, and stoichiometry should be conserved here. But if stoichiometry is not conserved, then there should be some interstitial site, some vacancy site at its cationic and anionic position. And these cases is happening in cadmium chloride doping sodium chloride. So when we dope cadmium chloride, cadmium is occupying the sodium site with two positive charges. This uh, these forces are extra sodium cation to vacant its position for compensating cadmium positive ion. So one sodium vacancy should be there, and chlorine ion should be um, moved forward to the interstitial side. Okay, that in the case of metal excess, color in sodium chloride. Okay, what type of behavior in sodium chloride is in the case here? That electron remains trapped in the anion vacancy. Anion vacancy should be there. There should be electron trapping with a chlorine. How electron will be trapped? From cadmium chloride to chloride ions. One electron is trapping, two electrons will be trapping, and where the chloride ion should go. Chloride ion should go to the interstitial side. Okay. But in the case of metal deficiency, what will be there? Just like the zinc oxide, cation and electron interstitial states will be filled, just like this. So this is not the case. Right? Okay. This is the figure of Schottky defect, that there's a negative charge missing, there is a positive charge missing, positive charge missing, negative missing, positive missing. Here negative missing means what? They are missing in pair missing, pair of positive and negative sides are absent. This is Schottky defect. We already know about this. Okay. So I have just taken an example from this source where it had been clearly discussed about how cadmium chloride is diffusing in sodium chloride. In this paper, in this research article, from famous research article in Mafotar, from this famous uh, researcher, they took they took the experiment of cadmium chloride diffusing in sodium chloride. They showed that how sodium cation is occupied, missing sodium cation is occupied by cadmium, and chloride vacancy is created also. So they are the missing site in paired vacancy. Okay. So the divalent ion vacancy complex. So this should be this paired valence. There was also a positive ion, and there also a positive ion. So in these cases, okay, in these cases, what happened? This types of structure has been happened, created there. So that uh, non-positive charges is transferring this side, and this is the vacant side. Cadmium is occupying this side. Okay. So maybe this type of um, reactions occurs in these cases. So sodium vacancies will be there, and cadmium interstitial will be there. Chlorine interstitial will be there. Going to the next question, question number 8. So now time is 7:13. Approximately 45 minutes are left. I think half we have reached half questions, half of the question solutions. And okay, next. If zirconium dioxide is doped with yttrium oxide, also the similar cases, how charge is balancing here, how what type of material will occupy in which position, everything is dependent here. So this is what type of reaction? Oxygen deficient oxide. We already have learned about zirconium dioxide. This is oxygen deficient oxide. Okay, this is oxygen deficient oxide. So this type of oxygen deficiency oxide, what type of behavior is shown? Their oxygen vacancy is formed or metal interstitial is formed, or both are possible. I already have told everything. Also, I am telling in this case also. So these cases are possible that oxygen vacancy will be formed, metal interstitial will be formed, or both are possible. In these cases, if your oxygen vacancy is formed, C2 plus will be there. So it will be metal interstitial, and this will be oxygen vacancy. Okay. So this is the case MO2, oxygen for oxygen vacancy in dominant cases. So this is the oxygen vacancy site with oxygen is removing out from this metal site. So oxygen vacancy should be there and oxygen vacancy and metal interstitial should be there. Okay, this is the concept that oxygen vacancy should be there, metal interstitial, metal at metal position should be there for oxygen cases. And if metal interstitial cases, what will be there? This will be 1 plus y, and metal interstitial should be there with 4 unit positive charge. Okay, in these cases, you can see metal interstitial should be there. Just like zirconium oxide, titanium dioxide, selenium dioxide, niobium pentoxide. All these materials show oxygen deficient oxide. All these metals or metallic oxides are considered as the oxygen deficient oxide. Oxygen deficient oxide showing oxygen vacancy as well as metal interstitial. Okay, metal will go to the interstitial side. Now you can answer that what is here doping. So when zirconium dioxide is doped with yttrium dioxide, so zirconium dioxide has a tendency to follow oxygen vacancy, and due to the formation of oxygen vacancy, extra yttrium anion cation will move to the yttrium interstitial. Okay, yttrium interstitial. So yttrium interstitial should be there as we are doping yttrium at the zirconium side. So zirconium would be excess. So yttrium will move to the interstitial side and oxygen vacancy should be there. In these cases, how charges are balanced, that for zirconium dioxide, it has +4 valence, and for yttrium oxide, Y2O3, it has +3 valency. Okay, so to balance +4, we need extra that yttrium ion extra yttrium cation. When we dope with extra yttrium cation, it will go to the interstitial site after compensating the zirconium cation. Okay. Okay, so uh, everything I have discussed. Okay, I am checking this. So this will be the case of oxygen deficient oxide. Okay. Now, question number 9. Question number 9. In case of non-stoichiometric oxide, such as metal oxide, just like non-stoichiometric, where oxygen vacancy, metal statisticial both can form. This question is similar like previous question. Okay, where oxygen vacancy and metal statisticial both can form. Okay, both are forming. What will be the defect reaction? What will be the defect reaction? First, where oxygen vacancy is creating means this type of reaction will be there. So this is true. And for metal interstitial reaction should be there. Means oxygen vacancy and metal interstitial both are present. Means this type of reaction is there. This type of reaction should be there. Here you can see that this is the oxygen vacancy for metal oxide like titanium dioxide, neodymium dioxide, zirconium dioxide, neodymium pentoxide, titanium dioxide, zirconium dioxide. Right. So in these cases, metal oxide will be there along with metal oxygen vacancy would be there along with metal oxide, which metal interstitial should be there. So aim at position M should go to the interstitial site with 2 unit positive charge, and to compensate 2 unit positive charge, 2 electrons should be there. Okay, unit positive charge, electrons should be there, but if two are present, what will be there? This should also be clear. So metal at metal side, metal goes to the metal interstitial side with 2 unit positive charge, oxygen vacancy with 2 unit positive charge, and these 4 unit positive charges are balanced by 4 electrons with half oxygens will be there. Here we have considered 2 oxygens so that 1 oxygen ion is okay. It depends on materials to materials. Here AMO is taken, here M2, MO2 is taken, and I have just taken to understand that to clarify the concept. So I have just taken MO2. Okay, you can see that metal vacancy, oxygen vacancy should be there and metal interstitial should be there. So both two options are correct. Where metal oxygen vacancy is creating by oxygen side. Okay, and if both are present, this is also correct. But not this D correct because here oxygen vacancy is not shown here. Not B is correct because here is not balanced. Here oxygen is not balanced. Oxygen site is missing. Okay, oxygen site is missing. So A and C are correct answer for question number 9. Okay. Okay. So we can now moving forward to question number 10. That titanium dioxide which shows oxygen vacancy as well as what? Oxygen vacancy as well as metal interstitial. Metal interstitial. Prone to possess oxygen vacancy. Okay. Along with oxygen vacancy, along with oxygen vacancy, metal interstitial should be there. Cl, TCl should be there. Okay. This is the concept. Along with oxygen vacancy, metal interstitial should be there. This concept you have to apply. So what will be the defect reaction? This is the equilibrium. These are the equilibrium defect reactions. In equilibrium defect reactions, three things must have to conserve: mass, site charge. Okay, three things should be conserved. First, this reaction do not telling about any oxygen vacancy or metal interstitial, so it should not be correct. First reaction. Okay. Then second, this is telling about oxygen vacancy and oxygen ion and four electron. This B option, for B option, this is balanced reaction. Okay. Oxygen vacancy is there for oxygen in oxygen side. This reaction is not containing the metal side. Okay, but this reaction is only containing the oxygen side. If it contains the metal side also, then the reaction should be different. Okay, we'll see in the next in the forward reactions that for C, oxygen here no valence site of oxygen is there, but titanium is showing interstitial site and oxygen and oxygen. Okay. Okay, first of all, first option is no oxygen valence site is there. Deficient oxygen the deficiency should be there, and metal excess due to an excess of cation. Okay. This is the deficiency defect. You already have learned it, and I already told, and this should be balanced there. Option B is balanced as oxygen vacancy for oxygen deficiency defect. Titanium, what will be there? Titanium at titanium side, and oxygen vacancy should be there, and half of oxygen. Means if titanium interstitial should be there. So if we are balancing all those, then oxygen site is balanced by oxygen vacancy and with two positive charge, that this is emitting out. Okay. And I have taken this from the sources, introduction to ceramics, that is clean body. Option C also balanced. You can see that option C is also balanced. So in titanium, it is showing metal interstitial defect. Okay. And this is compensating with 4 electrons, and oxygen is emitting ion. So that's, and D, in case of D, this is titanium vacancy. No titanium vacancy should be there. Vacancy would not be created for metal vacancy, should not be created in uh, um, oxygen deficient oxide. This also should be, so option D is incorrect. Only B and C are correct. B and C is correct. Correct. So, okay. Question number 10. Now we can move forward to question number 11. Okay. This is a problem involving Schottky defect. The fraction of Schottky defect in an oxide at 1000 Kelvin. So what is the temperature? Temperature is 1000 Kelvin. Okay. At a fixed temperature, a material is showing Schottky defect. This is the Schottky defect. Schottky defect means equal number of anion and cation are missing. This is anion, this is cation. Equal number of sites are missing. Okay, equal number of sites are missing here. Similarly, in these cases, equal number of sites. Okay, no, this is the case of, sorry, equal number of sites are there in here B negative, it V negative and A negative. Okay, so with A positive, B negative there will be there, and here A positive will be there, so this will form this. Okay, just I want to confirm that uh, equal number of sides are absent. Okay, then we call it as a Schottky defect. Okay, so this is the example of Schottky defect where uh, the defect formation energy here we can see that if we consider this defect, two defect has been created. To form the two defect, energy is 2.5 electron volt. Defect formation energy delta HF, defect formation energy 2.5 electron volt. Okay, this is the enthalpy of a reaction. So fraction of defect. So if we consider the fraction of defect as Ne, which is nearly equal to N, that is total number of atom site into exponentially vary, it will vary as an exponential form. We have already shown that delta HF divided by twice K into T. Okay. So this is the formula. This is the formula for calculating this type of defect. But we have to uh, put forward. So we can see that this is the Schottky defect calculation. This is the defect calculation formula for NX crystal, metal halide crystal, that n is equal to n into exponential of delta s by twice RT or twice KT. Twice KT. Okay. R, a value of R is 8.317 kilojoule per mole. When mole consideration is followed, and the value of K is 1.38 10 to the power minus 26 joule. Okay. Okay. If we consider it electron volt, 8 point something electron volt per Kelvin. Okay. So all these are the some values, but 2 kT should be there. Okay. So what is NS? NS is number of Schottky defects formed per unit volume. What is the enthalpy? Delta H is the enthalpy of defect formation. R is the universal gas constant, and T is the, or K is the Boltzmann constant. Boltzmann constant. And N is what? N is the density of ionic crystal compound into N, molar mass of the all the ionic crystal. Okay. So we have to find just Ns divided by N. What will be there? Okay. Fraction of Schottky defect. What will be the fraction of Schottky defect? Fraction. Fraction of Schottky defect is Ns by Nn. Okay. This is the fraction of Schottky defect. We have to find. To find it, what will be the value? Exponential value of what? Minus delta H divided by twice K into T. Okay. What is the value of delta H? Exponential of minus delta H. Value of delta H is 2.5 electron volt. Okay. And twice, what is the value of K? What is the value of K? Value of K is 8.6 10 to the power minus 5 electron volt Kelvin inverse. What is the value of T? T is 10 cube Kelvin. Okay, so electron volt will be emitting out, Kelvin will be emitted out. So only the number should be there, no unit should be there. So exponential of value of this minus of this, just calculate what will be happened. You can just calculate it. Okay. Okay, here is the calculator. Okay, you can calculate it by yourself. You can see that the answer will be in answer will be in 10 sorry, answer will be in 10 to the power minus 7 order. Okay, 5.6 10 to the power minus 7 order. The answer will be in 10 to the power minus 7 order. Okay, if time permits, I am doing at last at the end of the lecture. I will do at the end of the lecture, but answer will be this at the order of 10 to the power minus 7. Just put the value in this expression. You can easily find out the expression. Okay. Now question number 12. The reaction constant for defect formation. Okay, again, this types of defect, metal interstitial defect. This is the metal interstitial defect. Interstitial defect. Okay. Or oxygen vacancy defect. Just like titanium dioxide, zirconium dioxide, niobium pentoxide. Okay, this is very important defect concentration. So how defect concentration is dependent on metal interstitial vacancy and metal interstitial and partial pressure of oxygen. How K is varying. Okay, how K is varying here. Okay, how K is varying. Which option will be correct? So just look at this question. Already I have discussed about both AMI, metal interstitial vacancy are present when in the case of titanium dioxide, niobium pentoxide. Both will form. So in case of oxygen vacancy will be formed when both are present. Metal vacancy will be present, and these types of reaction I previously shown in the previous 2-3 questions. And this is the assumption that the oxygen concentration, metal concentration is 1. Just put the values of them and we can find K1 for oxygen vacancy, K2 for metal interstitial. Okay. Oxygen vacancy concentration. From this relation, you can find oxygen vacancy concentration. From this relation, you can find metal interstitial concentration and its contribution to partial pressure in K with K. Okay. You can find K2 value is Mi to the power 5 into PO2 into 4 to the power 4. How? Okay. For this, you have to consider this, that two vacancies should be created for what? You know? So in this reaction, if four oxygen, this is compensated by two oxygen vacancies. Two oxygen vacancies will be there, and four metal interstitials should be there. Okay, so this is the main equilibrium reaction, electrical neutrality reaction. Two oxygen vacancies will be there, four metal interstitial to compensate the electronic concentration. Okay. So electronic concentration of electron are compensated by two oxygen vacancy, four metal interstitials. This is very important. Okay. So when limiting case, when oxygen vacancy is much greater, we have considered complete ionization. When oxygen vacancy is much greater than metal interstitial, first case, when oxygen vacancy is much greater, what will happen? Oxygen vacancy will dominate. Okay. So if oxygen vacancy will dominate, then N equal to twice V, N should be, this terms will vanish. This will be 0. So N equal to twice V naught. So V naught equal to Ne by 2, Ne by 2, Ne by 2. Just put the value and you can find this type of relation for oxygen vacancy in this case. Okay. So it is varying with P to the power PO to the power minus 1 by 6. And if this case, I'm not going to details, just showing that in this case, this is varying with 10 to the power e to the power 1 by 5 to the power this. Wait, just uh, for these cases, for this case, what will happen if we um, NE should be what? 4, NE should be 4, MI should be there. Just put the value into this equation, you will find this type of relation. Okay, you will find this type of relation. So before going to discuss this type of variation with partial pressure of oxygen in first and second case, I am concluding uh, the question answer from this point, that what will be the value of K2 now? From this relation, we can find the value of K2. Just multiply with square of mi to the power 5. What will give? It gives K2 by 256 into PO2 to the power minus 1. Okay. So from here, what we will conclude, that K2 equal to Mi to the power 5 into 256 into PO2. So this is the required answer asked in the question, obtained from this relation where metal vacancies are dominant. Okay. Well, metal vacancies are dominant because complete ionization of the defects has been told, and here metal vacancy is dominating. Metal vacancy is dominating. Okay. So this is the case. Now I am just telling the first case where you can see that it is metal vacancy concentration is varying with this to the power minus 1/3. This is varying, oxygen vacancy is varying with to the power minus 1 by 6. In the second case, where this metal oxygen vacancy is metal oxygen vacancy is what? Much greater. Metal interstitial vacancy is much greater. Metal interstitial is much greater with oxygen vacancy. Then what will be the concentration of metal vacancy? Metal vacancy concentration varies with minus 1 by 5. And this is varying, oxygen vacancy is varying with minus 1 by 10. So minus 1 by 5, minus 1 by 10 for this case. And this case minus 1 by 6, minus 1 by 3. Just 3 into 2 equal to 6. Just 5 into 2 equal to 10. Just reverse of this. Okay. And you can see the variation of oxygen concentration with partial pressure of oxygen as this oxygen variation is doing as minus 1 by 10 when metal interstitial is much greater than oxygen vacancy, and when it is oxygen vacancy is much greater than metal. So these are two cases, and electron concentration must be dependent on the 2 of oxygen vacancy and 4 of metal interstitial. Okay, just their multiplication so that it is following this trend. Okay, now, so what will be the answer? Answer of this question will be this. Question number A. Question number B will be the answer. Okay. I am discussing question number 14 ahead of question number 13 because of some conception clear for partial pressure of oxygen dependency uh, in the defects, non-stoichiometric defects. Question is, if a ceramic is possessed with high partial pressure of oxygen, then what defects it likely to possess? Electrons, holes, metal vacancies, or oxygen vacancies. What defect it will possess? And we already have our with defect structure involving oxygen vacancy and interstice. Okay, so what will be the defect? Concentration with low partial pressure of oxygen, high partial pressure of oxygen, at intermediate partial pressure of oxygen, where oxygen vacancy is dominant, oxygen interstitial dominant, oxide is, for these cases, you already have learned this. At low partial pressure of oxygen vacancy is dominant. You can see oxygen vacancy is dominant. Corresponding reaction constant is this, how oxygen pressure is varying to the power half. When high partial pressure of oxygen, effect reaction is this, means oxygen interstitial should be there. Okay, oxygen interstitial should be there and corresponding hole should be there. Intermediate intermediate reaction, stoichiometric defects are formed via interstitial antifrankel defect. Okay, so this is the effect of intermediate partial oxygen pressure, where intrinsic ionization electron holes will be created and their corresponding is be there Frenkel reaction and intrinsic concentration, and their reactions are valid with this. This is the anti-Frenkel defect. This is the ionization constant and the oxygen vacancy and oxygen ion. Okay, everything is there for an intermediate PO2. So, what is the metal deficiency defect? We have already learned about that and how it is varying this type of reaction. Okay, and it is varying it proportional to oxygen to the power -6. And so, what will be the high partial pressure of oxygen condition? There should be what? High partial pressure of oxygen contains oxygen interstitial. Oxygen interstitial dominant, and so and hole will be there. So oxygen interstitial should be there, hole will be there. So one will be hole, and if oxygen interstitial should be there, if oxygen interstitial should be there, it will also implies metal interstitial, metal vacancy. Okay, metal vacancy, not oxygen vacancy. Okay, this will also imply metal vacancy. So metal vacancy should also be there, but not the oxygen vacancy, not the electron. In high partial pressure of oxygen, holes should contribute, metal vacancy should contribute. Okay. Okay, so we can now move forward to question 13. This is similar. This is based on the partial pressure of oxygen and its effect on oxygen vacancy, its effect on metal interstitial, and how they are varying in each condition: low partial pressure of oxygen condition, high partial pressure of oxygen condition, and everything else are clearly depicted in which diagram, that is called Brouwer's diagram. That is called Brouwer's diagram. So Brouwer's diagram has three regions. One is this left side region, this is the intermediate region, and this is the right side region. Left side region, which is high partial pressure of oxygen, high PO2 region. This is low PO2 region. High PO2 region always tells the P, means hole concentration. This is always occupies the electron concentration region. And how oxygen vacancy and oxygen interstitial. How oxygen interstitial, oxygen vacancy is varying, and at the central region both are constant, both are equal. This is the concept of the Brouwer's diagram. Already have told. This is the case where ionic defects associated with oxygen Frenkel defects dominating, and this is the case where ionic defects associated with intrinsic ionization dominating. In both cases, you can see neutrality condition that in here in previous cases this was constant. Okay, in oxygen Frenkel defect, oxygen vacancy and the corresponding oxygen interstitial with two unit negative charges, oxygen vacancy with two unit positive charges in Frenkel defect, oxygen and ion moving towards the interstitial ion in Frenkel defect so that it should be constant at stoichiometric crystal at the Bravas diagram where no partial pressure of oxygen will be there. Means moderate type of partial pressure of oxygen will be there. So in these cases, stoichiometric solid with intrinsic defect. This is the intrinsic defect, like Frenkel defect. It has discussed. Okay, and intrinsic ionization dominant also. So in these cases, so stoichiometric of solid should be valid there. It should not be oxygen deficient. It should not be oxygen excess. It should not be without any defect. No, it should not be there. Defect will be there, but intrinsic defect should be there. Okay, with maintaining the stoichiometry of the solid. Okay, so question number 13, 14, everything has been described with one after another. 14, then 13, due to the clearance of concepts. And we are now moving to the last questions. That is question number 15. Okay. Now we are entering into the dielectric ceramic. This is the dielectric ceramic. And barium titanate shows the dielectric properties. Okay. Where barium titanate can be formed in solid state method with barium carbonate, titanium dioxide and okay, in this by this two. Okay, so here titanium dioxide, what it shows? Oxygen deficient oxide, oxygen deficient oxide. Okay, so it shows oxygen vacancy as well as metal interstitial should be there. Okay, so everything we have learned about uh, titanium dioxide and its metal interstitial, and this effect. So in titanium dioxide, in barium titanate, what is the main factor? The main factor is the oxygen vacancy concentration. Oxygen vacancy concentration creates the conductivity. Conductivity of electric charge means the conduction of electron. Conductivity is higher due to this oxygen vacancy. We have to compress this oxygen vacancy. We have to decrease this oxygen vacancy. Okay. So what would be the procedure of decreasing this oxygen vacancy? To make a higher dielectric constant in barium titanate and to make it a higher energy storage density material, to make it higher polarizable material, to less is one procedure is to less its oxygen vacancy. And how we can decrease its oxygen vacancy? By doping with higher ionized material, higher ionization potential material like niobium pentoxide, uh, molybdenum oxide. Okay, but not zirconium calcium. They have less ionization potential. Okay, so this should be maintained, and this is the main concept in this question, that barium titanate having deficiency of oxygen, which results deficiency of oxygen. Okay, which results in conducting losses. Barium titanate show losses, conducting loss, dielectric loss. It shows dielectric due to its charge defect. Defect is present here. We have already shown oxygen vacancy, metal interstitial defect. Okay, so we have to decrease this charge defect. Which of the following can potentially be used appropriate dopant? What will be the dopant to make oxide more insulative? more dielectric, more insulating, more polarizable. Okay, for this a paragraph discussing about extent of non-stoichiometry, that magnesium oxide, aluminum oxide, they have highly stoichiometric pure oxide, so they have less, very small of reduction. We have oxygen pressure have very little effect also there, and oxides containing multivalent cation like titanium dioxide, barium titanate, strontium titanate, where titanium ion can be easily reduced to titanium 3 plus, creating oxygen deficiency of order 1 plus within limit stability. This is the meaning. So titanium ion, titanium 3, titanium 4 plus ion, it's reduced to titanium 3 plus ion. Okay, wait. Okay. So these points should also be. So nickel oxide, fluoride, and manganese iron, they are oxide with fraction of energy. So okay, we have already discussed more about this. So this point is main important here. They have deficiency. So what we have to uh, do to decrease this vacancy, we have to do niobium pentoxide. That is the barium titanate vacancy or oxygen vacancy. If we dot niobium pentoxide, then oxygen vacancy site would be diminished, decrease, creating on oxygen side, and niobium occupies the titanium site. Niobium occupies the titanium site. Niobium occupies titanium site with 1 unit positive charge. As niobium has 5 plus, so 1 unit positive charge should be there at titanium site, which to create titanium dioxide doping uh, niobium pentoxide, then two titanium sites should be there, would be occupied by two niobium ion with 1 unit positive charge. Titanium has 4 positive charge, it has 5 positive charge, so 1 unit positive charge should be there at each titanium side, and oxygen vacancy should be compensated by oxygen with this niobium pentoxide. That is why to compensate oxygen vacancy, to decrease the uh, electronic conductivity, we have dropped sodium niobium pentoxide. So niobium pentoxide should be one option, and along with molybdenum dioxide should also be true. So they also be true, but they will not be true because of their uh, because of their high purity oxide, and because of their extent of small reduction and oxidation. Okay, so these are all. I have discussed every 15 questions with brief concept so that you can answer the question. Although you all have learned in your lecture classes, I just repeated all of those. It is already 7:56. Mm, it is 2 hour class, so only 5 or 4 minutes are left. I told that if time permits, I will try to solve the numerical question with calculator. That this is the question. Okay, so just mm, so it will be multiplied as 2.5 into this will multiply as 100 divided by 2 divided by 0.617. Okay, this is uh, this is 50, or you can 10. Okay, So 25 into 5, 125 by 8.617. Okay. Just then do the exponential of negative of this. You can easily find 10 to the power 7 order, 10 to the power minus 7 order expression for this. Just do yourself. Okay. So that's all. Uh, we can now conclude. And okay, any question? If anyone have any question, you can tell any question. Anirudh, Ansu. Okay. Okay, now we can conclude here. Uh, See you next week on Tuesday at 6 p.m. Okay, that's all. Goodbye. Good night. So we can now conclude and end this meeting. Thank you for joining us. Okay, we can now conclude at leaving this meeting.